We have Carol in the series, and she's going to talk to us about the suggestive power of pictures.
Thank you. So, I'd like to thank the organisers very much for inviting me. I think I'm more of a kind of spectator to computing than a person who does computing. But I would like to talk about the fact that, well, I guess the best part of the last 25 or 30 years, a great part of my work has actually been inspired by looking at some of the amazing pictures that have been produced, mainly to do with kleinian groups. So, those of you who were here a few minutes ago, I asked the question, what's wrong with this picture? I mean, it's a beautiful picture. I'm not complaining about the colours and anything, but I will explain at the end of the talk why it's not quite the picture you might think it might be. So, anyway, I thought I would start, the first part of my talk is going to be sort of historical. So I would like to explain the project which David Mumford started, and a large chunk of which we wrote up in our book Inverse Pearls that I'm sure many people have seen. And I would like to explain something about the mathematics that came out of that. And then I will go on to two much more recent things, but which are in the same general area, where I have some answers, but a lot of unanswered questions. Right, so I think that probably everybody here knows kind of what I'm talking about here. So we're talking about limit sets of kleinian groups, so discrete subgroups of SL2C. So we're looking at Möbius maps acting on the Riemann sphere, and we are looking at the limit set, which is where the orbits of this action accumulate, and its complement is a union of Riemann surfaces. So this is all, well, it's not explained very technically, but it's kind of explained in this book. So, and just a reminder that these, I suppose part of the interest is that these groups not only act on the Riemann sphere, but they're isometries of hyperbolic free space, and so we can start studying kleinian group theory. So, at the time when Mumford first thought about doing this, the class of groups that were really understood were geometrically finite groups. That's ones which have a finite-sided fundamental domain for the action in H3. And the first thing that Mumford and David Wright did was they got going a sort of good computer algorithm where they could plug in some parameters for a group and churn out a picture of the limit set. Actually, the picture on the left actually was done by Kurt McMullen, who was interested around there at the same time. So this is a discrete group, and you see this beautiful limit set picture, and on the right you see what happens if you run their algorithm. Then the group is not discrete, it just goes kind of haywire. So they were astonished at the beautiful pictures that came out, which is why we started writing a book. But so to come to something sort of more mathematical, once they've got this basic algorithm going for drawing a limit set, plotting a limit set, Mumford had the idea of systematically studying parametrized families of groups which had some geometrical topological meaning. And obviously the best thing to do is to cut down the number of parameters as much as possible. So we really have to have a complex parameter. So he wrote down this one parameter family of groups, so generated by these two maps. C is the parameter. So C is a complex number, B is just a fixed thing. And these correspond to this manifold, which is a thickened punctured torus. So it's a punctured torus across an interval, but on the bottom boundary, one additional curve has been pinched to be parabolic, and that corresponds to this B generator here. And so the commutator, if you work out the commutator of these two guys, it's always parabolic. And you can show that whenever this group is free and discrete, this is what the corresponding hyperbolic 3 manifold looks like. And the point is that you can deform, by the general theory, you can deform the top surface and so generate a family of manifolds, but the bottom surface is rigid. So you've got a one parameter family of deformations, which is well understood from the classical theory of bears and alphors some input from masking. So here's what's going on. We have we're going to look at the parameter space of all the free discrete groups, the faithful discrete representations. Think of it as a subset in C. So it's kind of like, it's a bit analogous to the Mandelbrot set, which is, I think Mumford got his original inspiration partly from Mandelbrot generating wonderful pictures of Julia sets. So, as I said, this, sorry, let's go through that. Right, the top surface has got one component, and the bottom surface is a punctured torus, a triply punctured sphere. So we know the Teichmuller theory of this. We know what the boundary at infinity is. One thing, this thing is rigid, so it can't be deformed, and the punctured torus can be deformed. And if you just look at the conformal theory, it can carry any conformal structure that a flat torus can carry. So the space of these structures is the Teichmuller space of a torus, which is conformally the upper half plane. So this is sort of basic stuff. And Mumford set up the parameters, he chose them in such a way that the space of D, corresponding to the C parameter, would look as much like the upper half plane as possible. And he did that by various normalizations, notably this one. So he sort of put infinity at infinity, that's why it was chosen this way. And it's not hard to prove that the region above this line, imaginary part of C is 2, consists of free discrete groups. They're basically Schottky groups, but some of the circles are tangent, but it's easy to draw a fundamental domain, so you can see it's a discrete group. And it's also easy to check that you can't go down as far as the imaginary part C equals 0. If you do that, the group is plainly non-discrete. And before someone objects, there's a mirror image of this in the lower half plane, but it's just corresponds to turning the picture upside down, so we can just ignore that, be symmetry. So it sort of stands to reason there must be a boundary somewhere between these two lines, which repeats periodically with period 2. But the question is, where is this boundary? What's it like? And before Mumford and Wright got started on this, I should emphasize, nobody had a clue, really, about this boundary. I mean, maybe 1 point on this boundary was known. So, you know, you would get your PhD easily from finding one more point on the boundary. This was really hard because you have to somehow work with Teichmuller theory and quadratic differentials and deformations and so on, and somehow relate it to this parameter that sits inside the group Möbius maps in a very simple way, and this is a very hard thing to do.
Was it known that there was a neighborhood of the real line which was indiscrete?
Yeah, I think you can prove there's a neighborhood of the real line, right? Because you can, yeah, there's some easy things you can do, but somehow to actually pin down really where it is. Okay, but there was an idea due to Bears, and probably more in this context to Masket. They described abstractly a class of groups that they knew would be on the boundary of, just for general quasi-Fuchsian groups, on the boundary of these deformation spaces, called cusp groups. So if you take a loop on the boundary, and you imagine, and you're in a discrete group, and you imagine deforming the group by pinching this loop, and of course you have to discuss how are you pinching it. Are you pinching it in the sense of Teichmuller theory or kleinian group theory? But anyway, you pinch it. So Masket showed that if you pinch it right, you can travel through quasi-conformal deformations and come to a point that's on the boundary. So you can find groups which are on the boundary, and you can prove that if you have a group which is discrete, geometrically finite, and it's a faithful representation, and a particular thing happens to be parabolic corresponding to a loop on the torus, then this point must be a boundary point. So the idea is how you're going to find the boundary. You try and list all the possible loops on the torus, and you try to, so here are some examples that homotopy classes of loops on a torus. We can think of a flat torus, they're given by PQ wrapping around P and Q times, you can write down polynomial corresponding to these different things. So these are the group elements. So I'm not going to get into how you find these, but you can write down the group elements, and then you can say that the entries in these matrices in this particular family are plainly polynomials in C, so you can compute them, and then you can try and solve the condition for these polynomials to have trace plus or minus 2, which is a condition for being parabolic. But there is a glitch in this, because there are plainly, it's easy to see that these polynomials for P over Q turn out to be a polynomial of degree Q, which rapidly gets huge. So rapidly these polynomials have huge numbers of solutions, and there is no reason to think that most of these solutions correspond to any discrete group at all. In fact, they probably don't. Right, so there are a billion solutions, or 2Q or something, some large number of solutions, of which, well, only a few are likely to be on this boundary. And how do you know which they are? That was the problem. So, but because they had this systematic way of drawing limit sets, they could look at the limit set, you know, does it look like it's a discrete group or not, or does the algorithm go haywire? So they could systematically go through these polynomials and try and do it, and it was not easy. I mean, I want to emphasize this. It looks easy when you see it, but it was not easy. This is what they came out with. So this was a truly amazing picture. So this was the first hint of what this boundary, so this is like half a period of it, between 0 and 1. Then there's a mirror image, and then it repeats with period 2 all the way along. So this is 2i, and down here somewhere is the real axis, and this is this boundary. Well, there was no proof at all, but it looks jolly convincing. So this is the first example of suggestive power. And moreover, they found out that the limit sets of these groups, which they found, which look like they form a boundary. So this is not actually a continuous curve. It looks like it, but it's not. But all the things they found here, they all had the most beautiful limit sets that were patterns of tangent circles, and the patterns of circles relate to the continued fraction expansion of the fraction P over Q. So they got kind of hooked on that, and that's sort of what we wrote about in inverse curves. Right, but I want to talk about, well, it really looks like a boundary. What can you do with it? So I got interested in this with Linda Keene, and we played around with this picture a lot. Linda was one of the people who'd actually found 1 or 2 boundary points in a slightly different setting in the Bears embedding, but she kind of knew how to do the type model theory. We played with this picture for a long time, and finally, I don't quite know why, but we had the idea, let's get David Wright to take one of his boundary points where the traces, I think they alternate between plus and minus 2, I don't quite remember. Anyway, you take one of these roots here, where the trace is certainly real valued, and remember the polynomials are complex valued functions, so through that point it's going to have a branch where the trace is real, maybe it'll be a singularity, so don't put the lights on, I just draw. You know, remember what singularities are complex. If you have a complex valued function, then the place where the trace is real might look something like that, or it might just look like a single branch like that. Okay, but you asked Dave Wright, could he please start at these points, go in what seemed like the upward direction, and plot where the traces are real valued. And we did a few of these by hand, but you can imagine these polynomials, you know, it gets pretty hard to do this by hand beyond very low values of Q. We got this picture back, and I have to say this picture was one of the amazing things. We had no idea what these lines meant, but plainly there's a theorem here, maybe lots of theorems. Well, there's lots of theorems here, in fact. So just to say, it is not obvious that these lines would not have any singularities on them. It is not obvious that they don't cross. it is not obvious that they go off to infinity in such a nice way. They turn out to be asymptotic to the place the line real pi of c is 2p over q. Plainly there's something going on here. And we spent another year or so trying to come up with some explanation of this. And there's one obvious explanation that maybe, see, we knew there was a holomorphic map from the upper half plane to this region D, just abstractly. So this is holomorphic analytic, it's a holomorphic bijection. But of course, you know, you remember that boundaries of such things can be very complicated. You get all the theory of prime ends. But you could think to yourself, well, here there's some obvious lines which are these vertical lines, which somehow probably mean something in time-quantum theory. Maybe these guys are the images of these. We spent a lot of time unsuccessfully trying to prove that. So anyway, I will explain in the next slide the explanation that we finally arrived at as to what these lines are. But in the meantime, other people were inspired by this boundary picture. And so here we get some, well, here is one very famous paper. Kurt McMullen proved that whatever this boundary is, and he didn't know that that was the boundary, but he proved whatever the boundary is, these cusp groups described by Bears must be dense on the boundary. An amazing tour de force, this paper. Linda and I and Bernie Maskett proved something much less spectacular, but we proved that for each p over q, there would be a unique group, and this was a much more general theorem, and it's, in retrospect, it's very close to Mostar rigidity. You double the thing across the boundary, but it's a little bit more than Mostar rigidity. So it's sort of like an ending lamination theorem for cusp groups. And then Yair Minsky came along, and again, I believe, inspired by that very picture. So the question was, is this boundary really a Jordan curve, and is there a map from the circle, from the rationals, to this boundary, which is a bijection, continuous bijection? So Yair proved his famous ending lamination theorem for one-dimensional torus groups, I think inspired by looking at this picture, from which follows the consequences I said. And I have to say, I tried hard to prove this about boundary by other means, without success.
You mean the McMullen's theorem, or?
Sorry?
McMullen's theorem.
No, I tried to prove that the boundary was a Jordan curve and it was a holomorphic bijection by what doesn't really matter. Right. So what was it? So this was really without the rays, but what do these rays mean? Well, rays, it turns out you have to go into H3 and use this idea of Thurston of the convex hull boundary of a limit set. So you take a limit set in complex plane, Riemann sphere, and you erect its hyperbolic convex hull, which looks like this. So you fill this out with maximal circles, and above each circle you draw a hemisphere, and you look at the sort of outer intersection of all those things. And this thing, in hyperbolic geometry, these things are planes, and the lines where they intersect are hyperbolic lines. And it may be, not necessarily, but it may be that they intersect on lines which are the translation axes of particular elements in the group. And this thing can be proved, the quotient of this by the group is a copy, topologically, of the boundary. It's what Thurston called pleated surface, so there was theory about that. And it's easy to see. So here's another picture of a limit set where what the convex hull would look like is more obvious. This one is not quite the class of groups I'm talking about. It doesn't really matter. You see you've got a circle, and they intersect. And they intersect along a line, which is an axis of an element that has a fixed point there and a fixed point there. And because this guy translates along, leaving these circles invariants, it can't have any rotation around its axis, so it has to have real trace. So it turns out the rays in Dave Wright's picture, there's one for each rational number. It turns out to be the locus where this convex hull boundary of the top surface, bottom surface doesn't have any because it's a tricky boundary, the top surface is bent exactly along this axis, and of course all its images under the group. And as I move upwards along the ray that's here, the combinatorics of this arrangement of circles doesn't change, but the size and the intersection angles vary. And armed with that interpretation, it's possible to prove that these rays, now you need some geometry there, right? Once you've got an idea what they actually mean, you've got a hope of getting your hands on doing something. So we were able to prove that the rays are indeed like they looked in the picture. So this is all now becomes a theorem. Things I said. In particular, they end on the boundary, so these groups on the boundary, points that the two Davids found, are indeed unique cusp groups. So what looked like the boundary, we now know really is the boundary. All the things we wanted to know. So that's, and we called these lines pleating rays. And I just multiplied my talk. Anyway, I went off and we did some more examples. We found similar phenomena in many different one-dimensional examples. And later on, with various different people, I went on and was able to prove that you have a higher dimensional analogues of these rays, and you can say all kinds of stuff. Yes, sorry.
Yes, and from this theory, are you able to to state that it is indeed the image of vertical rays?
No, no, they're not.
They're not. Okay.
Right, right. You can. I think they stay within bounded distance of these, but they're not the same. It's this problem about the difference between the sort of quadratic differential view of type on this space and conformal structures and the hyperbolic geometry view, and they're not actually the same, but often they're like the hyperbolic structure on a pleated surface is a bounded distance away from the conformal structure in infinity, but they're not the same. So anyway, a huge amount of stuff came out of this idea, which I'm still puzzling about some aspects of it, but so that was the suggestive power of some pictures. So that's, you know, here endeth the first lesson, right? And the first part of my talk. What I want to talk about now is two very recent things that I have been interested in. And first of all, for reasons that you'll see a bit later on, I got interested in a different one-dimensional problem. So this is, you know, in some sense, you could have started with this problem just as well as the other one, and this is not why, the reason why we got interested in this I will explain later. But you can look at the groups, representations of a free group, given the three traces of two generators and their product, you can always determine, write down the matrix representation, determine up to conjugacy, and as I say, for reasons I'll explain in a moment, we reduce this, so here are three complex parameters, which is hard to do, but here you can reduce it in one particular way to a one-dimensional problem by just introducing this symmetry. The traces are the same. The three manifold now looks like this. There's no parabolic commutator, and let me first tell you what the pleating ray theory says for this particular picture. So you can reduce this problem, of course, by quotienting out the symmetry, which makes it a whole lot easier. Instead of trying to list all the curves on the boundary of this, or the symmetrical multi-curves on this, quotient out, and then you get an object which is, let me draw it here, it looks like a ball. So this is meant to be a free ball, and then you have two cone axes through here, which is where you when you quotient, you get sort of at the top and at the bottom, you get 2 order 3 cone points. So we have a threefold thing here, and a threefold cone axis here. So really, if you look at the boundary of this, it's a sphere with 4 punches. And Linda and I long ago had done a sphere with 4 punches, but they were parabolic. But anyway, the theory is almost identical, so that was easy to do. So you can enumerate loops on the boundary of this thing. If you cut it in half, so let me just draw a picture like this. So I'm going to just really draw the boundary. Cut it in half. You have, imagine a simple loop on this. You have a bunch of curves sort of on one side and the same number on the other side. So you have Q of these things, and then you put this together with a certain amount of twisting, which is P. This is a disk in the handle body. So if you twist by a fuller rotation, you come back to topologically the same curve. So curves are enumerated like this. And here is what we got. Here is the picture of the pleating rays. So now the rays are a bit different. They go off to infinity, a different asymptotic direction, but there is reason behind all this. And they look like, we prove they are like they look. Here is the boundary. The proof the boundary was a Jordan curve would be effectively, you need the ending lamination theorem for the handle body. But everything about this is now known. And so this is not the real reason we were doing this, but this is what comes out. Right, so I want you to kind of keep this picture in your mind, because the 2 things I want to talk about by complete coincidence both relate to this particular picture. So the first one is something that hasn't come out very well, but it's come out terribly actually. Anyway, if you look at a year ago the notices of the AMS, there is a rather beautiful picture on the front cover. Maybe some of my later pictures will show better. In which you see lots of rays, and then you see lots of red dots and lots of blue dots, and the thing on the cover tells us that this picture is somehow connected to Gavin Martin's search or find of the minimum volume hyperbolic 3 orbifold, which was a massive project carried out by Gavin Martin and Fred Gearing and Colin McLachlan and Alan Reed and many people over many years. So finding the minimum volume orbifold, and somehow this picture is related to it. Well, so it's a picture of rays, and actually, if you had a better copy of it, if you look at it, it's exactly the same as these rays, which is why I looked at it. And Yamashita is one of my co-authors who draws beautiful pictures. We'll see more in a moment. So he drew this picture. So, okay, what is this picture about? Right. Now, what are these dots? Because these dots are, it's a shame you can't see, but if you look closely at the picture, it looks like all these dots are on the rays. So you try to understand this, and you look at the article, and it tells you something, but I don't think the person who described the picture was the person who made the picture. Anyway. Right, so what are the dots? Right, this is a new thing. So it turns out, I don't have time possibly to go into Gavin Martin's search. This is another phenomenal computer-aided achievement. But anyway, in his search for these groups, lots of the groups he needed to look at, sort of check for their volumes, turn out to be arithmetic. So just think, what does this mean? Well, roughly it means the entries in the matrices are things like square root of 2, or the square root of 2 plus the square root of 1 plus root 5 or something, and the group is discrete, and a quotient has finite volume. Right, so that's let's take that as a definition of an algebraic group. And here is a great condition, great sort of, you can sort of, this looks extremely difficult to check, but here is one very useful criterion that applies in our particular case. So if we take the trace parameter x that I had before, so I don't know what I was calling it before, but this x I'm talking about is the trace of A, which is equal to the trace of B, which is equal to the trace of AB. Gavin had a slightly different parameter, but it sort of differs by x minus 2 or x plus 2 or something. Okay, so here is a test for a group being arithmetic. Yes?
So those A and B, those are not actually the same as the A and B.
Yeah, they're just, oh, okay, yeah, sorry. You're right, these are not the same A and B. These A and B, yeah, oh,
Right, this
sorry,
A and B
no,
is
you
identified.
said something very good. This X is true, but that A and B are these two rotations. So I'm mixing up two different things, sorry, okay. I don't think it really matters from, okay. But yeah, the A and B there, because it says it's a group with A cubed equals B cubed as the identity, is the group associated to this. And of course you figure out what the connection of this parameter with this parameter very easily. Right, okay, anyway. It turns out that the parameter we're interested in, let me say, has to be, in order for this to be an arithmetic group, we need this x to be the root of a monic polynomial, integer coefficients, and it has to have all its roots real in this particular interval, except for one pair which are complex conjugate, and those will represent the groups that we are actually interested in. Right, so this is, to me, this is kind of magic, this result. So, right. So I'm not saying all of Gavin's groups had to be like this, but this sort of enters into the problem. So here again, still come up badly, but here is another version of the picture. I think it was Colin McLachlan who asked probably Fleming and Ring to, if they could find all the polynomials. So this is a very sort of restrictive condition on a polynomial. It turns out that there can only be finitely many such polynomials, which is not, to someone who's not a number theorist, obvious at all. But using some clever number theory tricks, you can bound the number of polynomials, and you can find them by, computer search and clever number theory combined. And you list all these polynomials. The one thing that they didn't do was they didn't know which have finite volume quotients and which have infinite volume quotients. And of course, Gavin only cares about finite volume quotient. If it's got infinite volume, obviously it's got minimal finite volume, so check it, right? But how do you know which ones those are? Well, I don't think he had a particularly efficient way of doing that, but Yasushi, being an expert on drawing pleating rays, knew exactly where the boundary of the discrete, the free discrete groups which have got the infinite volume ones are. Those are the ones outside this kind of grey thing in the middle. So Yasushi coloured the infinite volume ones blue, the ones sort of overlapping in the pleating ray region, and the ones that are inside this grey bit, he coloured them red. And it turns out that the minimum volume one that was discovered happens at this particular parameter value, which is, you can see in algebraic, it's an algebraic number field. Right, so...
Even if the pair of complex conjugate roots can become large, still there are finitely many such polynomials?
Yes, you can bound the number of polynomials. This fact that the real roots have to lie within this bounded interval, a small bounded interval, enables you to get a handle on a bound. It doesn't seem obvious, right, at all. But anyway, this clever trick that enables you to bound.
But piece numbers have the same property, but...
Well, but you're bounding
you
within a certain
pair,
particular interval that's quite small. I think that's really what it comes down to. That. I mean, you kind of, you know, I have read their paper, but I can't explain. It's very clever.
Is something about heights, or is it more arcane?
There is a clever trick about the bounding the number of roots that right now escapes me. To do with, I can try to talk to you afterwards. And then you show it's finite, you still have to find bounds so that you can conduct your search. And somewhere out there on the web, there is their listing of all these polynomials. And of course, then it still takes some skill to find all these roots computationally. So, one thing that's, okay, so if you look at this picture, there's an interesting feature. Well, first of all, you can see these green lines have been continued, or some of them have been continued, inside this region where the groups are no longer faithful. They're no longer faithful representations. So what's going on there? So these lines are where the trace of a particular group element happens to be real valued. It comes down, in fact, it's always -2 on this boundary, at this boundary point. If you go on, continue the ray, you run into the region where the trace, it sort of goes on increasing from -2, and you can run it along until you get to the value 2, which means you've actually got to the place where this thing is the identity. So you can continue the ray, and actually you could continue all of the rays, but most of them, the continued part is tiny. It's so short, it ends so near the boundary you don't really see it. But that's what these inside extended rays are. But once you're on one of these rays, you've got an element which is either it's elliptic, so either it's not a free group or not a discrete group. Right, so what Yosisi did is simply plot his dots on top of the rays, and it looks like, as far as you can see from the picture, that all the dots are on the rays. So I don't know why this is. This is one suggestive picture. But if you just saw a list of these things, I don't think you would see. But I can say something about what's going on along these rays. So I got interested, well, you know, okay, the ones that are on the rays, what's going on? So we know what's going on along the ray when it's actually a pleating ray. So when it's sort of in the part covered by the real pleating rays, what's going on is that the, so let's say the trace of G, which depends on P over Q, is greater than 2 and it's real. Sorry, greater than, actually it's going, let's do it right, it's less than -2. So it's decreasing to infinity as you go out along the ray. What does this thing look like? We've got a pleated surface in the boundary of the convex hull. It's a 4-punctured sphere like that, cut along a curve, so it falls apart into 2 pieces, but it's the same picture as what I drew there. It looks like this. And we've got an order 3, another order 3. These will be conjugates of the A and B that we started with. And we've got, let me just now call it G. And so we've got a sphere with 2 order 3 things whose product is this thing. And on this thing, this side, it's the same, but just different conjugates. And they glue together. So that's what the convex hull boundary looks like when I'm sort of far out in the picture. Now what happens, okay, on the boundary at infinity, what you see is like one of the pictures I drew early on. You see 2, when you lift these 2 guys, you see 2 overlapping circles. Well, you know, this thing is not really there, and the limit set is a subset of this stuff here, and then of course the picture repeats everywhere. And this is the axis of G. So that's what we see. Now we carry on down the ray. So, oh, okay, so let me say this right. This thing is a hyperbolic surface. There's a little Fuchsian group called G sub R or G sub L, generated by 2 things. 2 order 3 elliptics, if you just look at the boundaries, product happens to be hyperbolic. So it's a Fuchsian triangle group. Maybe I'll draw a picture of it here. So it sort of looks like it has a fundamental domain. It looks something like this. And actually there's an obvious order 2 symmetry, so you could think of it sort of like this. So you can think of pi over 2, pi over 3, and infinity. So you can make a little sort of infinite-sided triangle like that out of it. So what happens when I come down to the parabolic point? Well, of course, what happens is that this guy is pinched to a parabolic, so it gets infinitely long, like this, and this picture becomes 2 tangent circles, Mumford's tangent circle picture, and this picture comes like a triangle like this, which again has this symmetry, so 3 to infinity triangle. Okay, so what happens when I go below that? Well, plainly what should be happening is that I should be getting, G should become elliptic, these guys should come apart, so here's G, and 3, 3 again. So my 2 circles come apart, and what I get here is a picture like this, and I get 3, 3 to n. Well, if I want a discrete group, let's forget indiscrete groups. If I want a discrete group, G better be elliptic of order n, so I get a 3 to n triangle group, and I'm sure everybody knows you can only get one of those if n is greater than or equal to 7. So as I'm going down this extending grade, I should get that. And if I think about it, the region underneath these 2 circles persists, and it forces my group still to have infinite volume. What happens when I hit n equals 6? Well, 3, 2, 6 is a Euclidean group. So you think for a while, this picture goes away. So what happens is that these 2 circles become points. And all the axes of all these elements, which, so I didn't draw the axis of G. The axis of G is sort of like this. So it changes from that to that, and it rotates around here. And then there are 2 other axes, an order 3 axis and an order 3 axis. Okay, if these degenerate to points, these 3 endpoints have to come together at infinity. So you think about it, what that means is at infinity, I've got a fixed point for a little group, and instead of being hyperbolic, it's now a Euclidean group. But that can happen if you can fix infinity with a 2, 3, 6 Euclidean group, like that. So on the horror here, at this point, you would see that group. And then I keep going to 5, 4, 3. Well, we know what these are. These are spherical groups. And what happens is that instead of being out at infinity, these fixed points move inwards in a symmetrical way. So you get fixed points inside, like that. And so you can have a spherical subgroup with some singular axes meeting inside a hyperbolic group. And so you get this proposition that tells you if you want a hope of finite volume, on one of these rays, you must either be in the 6, 5, 4, or 3 cases, like that. Okay, and then you go back and you start looking at the picture, following down the rays, chasing up your cis dots and trying to compare it to Gavin Martin's lists of groups. And for example, you find this, you find the minimum volume group is exactly where the 1/2 element happens to have, corresponds with the 3, 4, 5 spherical subgroup. And if you study what we know about the geometry of this orbifold, indeed it does have exactly such a subgroup. And you can go on different rays and you find the next smallest group like that. It's sitting there on the ray, And you find kind of examples of all these different things, and then there's some sort of degenerate cases as well. So it's kind of fun going down these rays, but it gets rapidly too difficult to do it very far by hand. So this question, I think, if you understood arithmetic groups, might be very difficult. But remember, the kind of parameter that we're talking about down the ray is not the same as the base parameter. It's related to it by some polynomial equation. But one question I have is, Gavin Martin's search gets extremely complicated. He uses a sort of mixture of kleinian group theory and complex analysis to eliminate more and more groups. Can we somehow use this idea of going down the ray to come upon interesting groups faster? Do all these groups, do all these dots really lie on these rays? And if they do, why? Not obvious to me. And does every discrete finite volume group lie on a ray? Search. So a bunch of questions which I can't answer. Right. So I have a short time left to do the other example I wanted to talk about.
Can I ask a question?
Yes.
So when you're moving inside the gray region on these rays,
Yeah.
there's only this finite number of discrete things.
Yeah.
Can you think about the intermediate things in terms of some kind of combinatorial?
Yeah, they are co-manifolds. So I confess, I have not written down these properly in terms of deforming co-manifolds, but that's plainly what's going on. And in fact, if you look at the proofs about deforming co-manifolds, you come to certain points, I guess Craig knows about this, right? You come to points where things degenerate. And you can see all these things going on that they say might happen. They happen in this example. So, and there is some work by various people, Sakuma and other people, doing something a bit similar with this on extended rays outside the Riley slice. So it's not a completely new thing. There's a whole lot of stuff to look at here. Right. So, completely different thing, but just by chance, this is why I was interested. Certain so I should write up who. So this is work I've been doing recently with Sertan, and Yususi Yamashita. Okay. So they got interested in something that we call the Bowditch or VQ condition, introduced by Brian, in order to give a combinatorial proof of McShane's identity. But that's not really relevant to us now. So this is a condition on a group that may or may not be discrete, and it's something to do with the primitive elements in a SL2C representation of the free group on two generators. So his condition says that everything primitive elements should be loxodromic, and only finitely many traces should be less than or equal to 2. And we consider this set of things satisfying these conditions. It's easy to see if the group is geometrically finitely discrete. It holds, and Brian made a conjecture, which is still open, about when the commutator's parabolic. And we decided to do a systematic computer investigation, or they decided to do systematic computer investigation. So if you plonk down, remember I said 3 traces determine everything. If you plonk down, these are traces of a pair of generators and their product, like that, this trace relation enables you to fill in the other places. So for example, this one would be u, v minus w. So this corresponds to u, v, u times v, and this gives u times v inverse. These are all the moves that get you all the generators. So you can have, here we'd have the generator u squared v, and its trace would be u, v minus w. Yeah. Right. So you can see you can fill in this thing, that you get all the generators, generator pairs this way. You can fill in the traces in the complementary regions. And Brian's results lead you to a good check. You can check sort of computationally whether these conditions hold. So Brian's idea is basically you say I have a setup that looks like this, Z, U, V, W. If the modulus of Z is greater than the modulus of W, I put an arrow. If it's equal, you can choose which direction you put the arrow. Just do that, and you prove a little lemma that says, well, certainly if all the things are doxydromic, if I have two arrows coming out, this picture implies, and let's call this W, it implies that the trace of W is small. So these guys, if they're loxodromic, it means that they have short translation length and a considerable amount of rotation. Right, so you can turn this into an algorithm. Basically, this little lemma says if you can follow arrows down this, paths down this, and you will eventually, if you are in the Bowditch set, you will come to a sink, and it also says, the theory says there will be a finite subtree of edges such that everything else lands in this finite subtree, and you can compute and test is there a finite subtree. That's a test for being in this set. So here is the picture. So same slice we did. Here's the discrete rays, but this stuff that's blue here is stuff that satisfies the Bowditch condition, but which is not obviously discrete. So this was the first time you got something that is manifestly.
Can you remind us why it's not doesn't have the reflection symmetry about the?
Because the reflection symmetry came from the symmetry in that 3-ball, and this setup does not have the same symmetry. Let's discuss it afterwards. It does not have the same symmetry. So, discuss it afterwards. Okay? You work out the symmetries, and it doesn't have the same symmetry. Okay. You can also do plots when the trace of the commutator is parabolic. In fact, Yasushi draws the discreteness regions in such cases by using this algorithm, and it looks right, but there's no proof. Right. So my student Damiano Lupi succeeded in proving there's a region around the boundary here, an open set, except with one or two exceptions, an open set around the boundary, where points are in the Bowditch set, but plainly quite a big set. So here is another amazing picture, really what I want to end with. So in the course of doing this, before he did this picture with these rays, which are the correct rays, he did another thing, which if you know, it's quite a natural thing to do. You take what, there's one of these for each P over Q, so you take all the primitive elements are indexed by P over Q, so you take all the primitive elements, figure out their traces, figure out where the traces are real valued, and you plot, you look for a branch of it coming in from infinity, and you draw the ray, and you think, oh, I'm going to be finding the pleating rays, and he did it, and he came out with this amazing picture. It's not super high resolution, but it kind of shows, it looks very much as if these rays, which I decided to call Y rays for the Yasushi, Y rays appear to fill up the Bowditch set. So I've been thinking about this picture for some time. What are these rays? Because they are not the correct pleating rays. If you go through the theory, these primitive elements do not correspond to simple closed curves on the boundary of the Hammer body that we started with. So they're not the right things to be looking at. It's kind of confusing, but they're not. But in the course of trying to prove this, so you kind of need to ascribe a geometrical meaning to these guys. So I have some conjecture, but no proof yet. But in the course of it, it became clear that there was something that kept entering in. So Yaiminsky has a condition that applies to non-discrete representations of the free group called primitive stability. And Brian has this condition that I've told you, and it's been a question around for a while. What's the relation between these two? It's obvious that is implies this one, but the other way around is not obvious. So, inspired by thinking about this picture and some of the, what I was doing to try and give a geometrical meaning to these, at least I proved something. So it involves a new condition, so let me end up telling you what this new condition is. So here are two lemmas, and then you will see what's wrong with the symposium poster. Here is a lemma. I don't know if anybody knows this lemma, tell me. So you take a pair of generators of the free group. The lemma says it's conjugate to a unique other pair, sort of simultaneously conjugate, such that both of these two are cyclically shortest, and they're both palindromic with respect to either the pair AB or this pair or this pair. So palindromic is something like Abel was I, ere I saw Elba. Like that. I'm going to end up with one that's not. I want to end up with one that could be a. Right, there's one that's palindromic and happens to be primitive. Okay, so I'm saying any pair of primitive elements you can go into this form. And then there's a nice geometry about palindromic words. So if I draw the axis of A and the axis of B, this is quite a general thing, and I take the common perpendicular of them, then if I do if I do the map that sends A to A inverse and B inverse, that sends these two axes to themselves reversing orientation. So it sends this common perpendicular to itself, and it's easy to check that if you have a word, so if this word is W, then the axis of W goes through this common perpendicular and hits it perpendicularly if and only if this word is palindromic. Nice little lemma. Okay? So, what's this condition of bounded intersection property? It is that if you take the three axes of A, B, and AB, which is another thing that you always do in hyperbolic geometry, and you draw their common perpendiculars, so you thereby make a hexagon, then what I'm saying is that every generator pair is put in the form so that both things cut one of these three axes perpendicularly. So each one cuts two of these axes perpendicularly. But of course you have to conjugate to do that. But anyway, so you get zillions of these primitive elements cutting here perpendicularly. If they all cut within some fixed bounded interval for these three pairs of axes, that's what we call the bounded intersection property. So that's a nice property, and my conjecture is that these rays, the PQ ray is the ray on which the PQ curve is maximum along this interval. So here are some theorems ongoing, and so let me now finish by telling you what's wrong with this symposium poster. So this lemma, sort of proved by Linda Keane and Jane Gilman, but I wasn't very satisfied. So I was wandering around my house, trying to think of a sensible proof, and my eye fell on the symposium poster, which is stuck up in my kitchen, and I thought, we prove it by induction on this tree, right? On this coloured tree. So that's what the picture suggests, so you sit down and try and do it. So what do the colours mean? Well, what should the colours mean? We've got these three triples of generators, we've got three classes of rational numbers, those which are like this, mod 2, and those which are like this, and those which are like this.
There are two possible trees. I decided to want to do one where a parabolic alternates both between all three colors instead of just two colors. You could draw the other tree.
Yeah, but if you wanted to Okay, right, that's true.
Right, so this
It's not wrong, but
This was
it's...
a choice.
But if you want to prove by induction this theorem on the tree, then you want it to be so that every time these two guys of this type are adjacent along an edge, then you would like the edge to be a constant colour, right? That seems natural. And if you do it that way, in this picture, the cyclic order of colours around the vertices is constant. If you want to do it in this way, so for example, you want 1/2 and 3/4. This one, so it's not doing it this time. Anyway, you want these always to be the same. Then you want, what happens is that the colours round the parabolics, around the horocycles, just alternate. So you go green, blue, green, blue, green, blue, right? And then you see that to get from one red edge to another red edge to kind of make your inductive step, you march around a bunch of green, blue, green, blues, and then by a miracle, it's easy to write down the proof. So thank you for the people who decided to make this picture. That's your hand up.
Are there any questions for the speaker?
Could you show us the PIP condition again? Because it was a little alright. Just leave it up. Thank you.
So, okay, I am working with this condition would work in any short group. I mean, any representation of F2. But in the particular case of the diagonal slice, there's a great deal of symmetry. So if P over Q has a certain relation to this condition, then so does Q over P, and P minus Q over Q, and so on. So it's like this sort of, if you worry about what are the maximum, so the condition is that along, say, this line, all the palindromic primitive guys hit in a bounded region. Actually, Linda Keene and Jane Gilman looked at this condition, but not for primitive elements, but for all elements, and they proved that a group is discrete, if and only if, discrete and geometrically finite, if and only if the intersection of the palindromics along this thing is within a bounded interval, which is sort of what gave me the idea.
Could maybe we turn on the lights and see the picture that you're drawing?
If somebody would need to do it.
Is over here.
Red. So what's the statement of the PIP?
So you draw the three common perpendiculars between the three basic axes. You draw the triple of axes of A, B, and AB. And you draw their common perpendiculars. So let me put, and they're sort of like the analog in 3D of the elliptic fixed points, the three elliptic fixed points. So you get these three common perpendicular axes that are invariant under, which are invariant under this, and which have the property all of these guys will go through that perpendicular. Okay, and the condition is there exists a number m so that every palindromic word that does go perpendicularly through the elliptic thing of A and B is within distance m of base uniformly. So it's kind of uniform control on the position of not all the primitive axes, but a special subset of them. Right, because not every primitive element, you can do lots of cyclic conjugates which are not palindromic, and then you have no control. The problem with trying to prove BQ implies primitive stable is that you exactly somehow don't have the control. So you have, like you take a very long word W, primitive stable is to do with drawing this broken geodesic that corresponds to W. So 0, A 0, A squared 0, A squared B 0, and so on, and we come to W 0. So primitive stable says that the collection of all these broken geodesics for all primitive words is uniformly quasi-geodesic. So it's something about bounding this distance doesn't get too small, right? The problem is that you have to somehow control what happens to all this stuff in the middle. So it could be, it goes along nicely for a bit, and then suddenly it goes up here, and then it comes down again, and then it goes along here, right? And here is 0 and W0, and you think, well, okay. But then you say, oh, but these primitive words are very special because they're built up by sticking together lower primitive words.
You can always conjugate, you can always rotate to get to be palindromic.
Yeah, but if you didn't know that condition, right, you just stare at these and you say, well, here's a sub-primitive word. So supposing I prove that guy has got some quasi-geodesic. Individually, they're all quasi-geodesic. So, you know, I can handle this, I can handle this, I can even handle this, right? So you say, okay, there's a little sub-patch here and a sub-patch here, and if I stick them together, but somehow, it's what my student Damiano was trying to do this for a long time. Every time you try and do it, somehow little bits kind of pop out, because how do you know between this patch and this patch, maybe there's a sharp bend. And somehow the point of this condition is, it's enough to control the position of enough things that you can avoid it coming out. So I can explain it. I mean, I'm not telling you anything about theory. That's not good.
Any other questions? Okay, let's thank our speaker again.